Okay, welcome to chapter 17, section 1. Let's get into the key ideas here. What are the different kinds of electrical charge? How do materials become charged when rubbed together? What force is responsible for most everyday forces? So let's talk about electric charge. What are the different kinds of electric charge? An object can have a negative charge, a positive charge, or no charge at all, which is called neutral. Electric charge, basically defined, is an electrical property of matter that creates electric and magnetic forces and interactions. So like energy, electric charge is never created or destroyed. And you should know from previous science classes here that like charges repel and opposite charges attract. Electric charge depends on the imbalance of protons and electrons. Electrons being negatively charged, protons being positively charged. Neutrons are neutral. So negatively charged objects have more electrons than protons, and positively charged objects have fewer electrons than protons. So let's watch a little video here on electric charge.
Electric charge is a property of matter that generates forces between objects. We refer to charges as being positive or negative. Positive charges are marked with a plus sign. Negative charges are marked with a minus sign. Each of these lightweight table tennis balls has been given an opposite charge. When we release these balls, we see that they move together. Opposite charges attract each other. When charges are the same, however, they repel, regardless of whether the charges are both positive or both negative.
Okay, there, so you see that when suspended, no other forces acting on them except for gravity, they'll go apart. If they're like charges, either both positives or both negatives, they'll spread apart. And then if they're opposite charges, they will attract each other. So the SI unit of electric charge is called the coulomb, capital C. A proton has a charge of positive 1.6 times 10 to the negative 19th coulombs. An electron has the same value but just negative in its charge. The amount of electrical charge on an object depends on the number of protons and electrons, and the net electric charge of a charged object is always multiples of 1.6 times 10 to the negative 19 coulombs. That's simply because you've either gained or lost electrons. Electrons have that specific value, so they'll be in multiples of that specific value. So let's watch another little video here on the characteristics of electric charge.
There are two kinds of charge, known as positive and negative. Like charges repel each other, and unlike charges attract each other. Electrons can be transferred from one object to another. The number of electrons gained by one object is the same as the number of electrons lost by the other object. No charge is created or destroyed. Electric charge is conserved. When an object is charged, its net charge is always a multiple of a fundamental unit of charge equal in magnitude to the charge on the electron. Because of this, charge is said to be quantized.
Okay, so you see here in the last part of this video, they have the same number of positive and negative charges in the sphere here, and they cancel each other. They've paired them up and they cancel each other out, except for the three electrons, which do not have a positive partner per se. So this sphere has an overall negative 3 electron or 3e charge to it, which is multiples of that 1.6 times 10 to the negative 19th coulombs. Alright, so transfer of electric charge. How do materials become charged when rubbed together? So when different materials are rubbed together, electrons are transferred from one material to the other. The direction in which the electrons are transferred depends on the materials themselves. Conductors are materials that allow charges to flow. Insulators do not. Just like with heat energies, conductors allowed heat to travel very well. Insulators did not. Same thing with electricity. Conductors have allowed charges to flow very easily. Insulators do not. So an electrical conductor is a material in which charges can move very freely, and electrical insulator is a material in which charges cannot move freely. So charges can move within uncharged objects. So the charges in a neutral conductor can be redistributed without changing the overall charge of the object. Although the total charge on the conductor will be zero, the opposite sides can have what's called an induced charge, like we saw in the previous sphere. When they brought the rod close, all the positive charges went to one side and all the negative charges went to the other. That's called an induced charge, even though the net charge on that sphere was zero before it was touched by the rod. So let's look at electrical conductors and insulators.
All materials can transfer some charge, but some do so far more efficiently than others. Conductors are materials in which electric charges move freely. Most metals are conductors. Insulators are materials in which electric charges do not move freely. Examples are glass, rubber, silk, and plastic. It's possible to add extra charge to an insulator, but there is little tendency for the charge to move into other regions of the material.
Alright, so induced charges. You see here a picture again where if you bring a charged rod, in this case it's a negatively charged rod, is brought near an object that is neutral. See, there are 4 positives and 4 negative charges. So they cancel each other out, so the knob would be actually neutral in charge. But since you brought a negative rod close to it, even though it's not touching, the negative charges will be repelled, so go to the opposite side, and the positive charges will be attracted toward the rod. So you have what's called an induced charge on this doorknob. Alright, so objects can be charged by contact. Transfer electrons from one object to another can charge objects, and objects charged by touching a charged object to a neutral object are said to be charged by contact. Objects can be charged by friction. Charging by friction occurs when one material gains electrons and becomes negatively charged, and the other loses electron and becomes positively charged. This is like taking a balloon and rubbing it on your hair. That's done by friction, where one gains electrons and one loses electrons. So your clothes are charged by friction as they rub against each other in the dryer. If you ever done that, take clothes out of the dryer and they get that static cling, and they stick together because of that static electricity. You can also do that sometimes when you ride shoes on. If you've sat in a car for a while and rubbed your feet on the floor of the car, you can charge by contact, and then when you get out you shock somebody or shock the door. Happens. So charging by contact, when a negative rod touches a neutral doorknob, electrons move from the rod to the doorknob, and then the transfer electrons to the metal doorknob gives the doorknob a net negative charge. So let's see charging by contact.
One way to charge objects is by placing them in physical contact with another charged object. Consider a Van der Graaf generator, a device used to produce electric charge. Once the generator has a net electrical charge, if you place your hand on it, electrons will flow onto your body. If you are not insulated from the ground, the electrons will naturally flow from your body to ground, in this case to Earth. If you stand on an insulator, such as a wooden block, the charge will accumulate on your body. You will notice that strands of your hair stick out. This is because they all have the same electrical charge, and like charges repel each other.
Okay, so transfer of electric charge continue. A surface charge can be induced on insulators. So when a charged object is brought near an insulator, the positions of the electrons within the individual molecules of the insulator change slightly. So one side of a molecule will be slightly more positive or negative than the other side. In this case, molecules are said to be polarized. So what force is responsible for most everyday forces? The electric force at the atomic and molecular levels is responsible for most of the everyday forces that we observe, such as the force of a spring and the force of friction. So electrical force is the force of attraction or repulsion on a charged particle that is due to an electric field. So the electric force is also responsible for effects that we can't see, like the bonding of atoms to form molecules is due to electric force. Electric force depends on charge and distance. The electric force between two objects is proportional to the product of the charges on the objects, and it's inversely proportional to the square of the distance between the two objects. If you'll remember back to our study of gravity, the force of gravity was a constant with the mass of one times the mass of the other divided by the distance between them. And as the masses got larger, the force got stronger, or as the distance got larger, the force got weaker. Same kind of deal here with electric force and electric charges, is that if the charges are greater, there's more force. If they're farther apart, there's less force. So electric force acts through a field. An electric field is a space around a charged object in which another charged object experiences an electric force. And a way to show an electric field is by drawing electric field lines. And basically electric field lines just point in the direction of the electric force on a positive test charge. So what happens is here you have a positive charge, and these lines indicate if I took another positive charge, like a test charge, and put in this particular area here around this, that positive charge would be pushed away from this fixed positive charge here in the center. That's why the lines go away from positive charges. Now in the other one, in a negative charge here, if we placed a positive charge here, it would be attracted toward the negative charge, so it would be drawn toward it. So that's why the arrows move toward negative charges. Alright, electric field lines never cross one another. These field lines near two like charges point away from each other and show that charges repel each other. Field lines also show that both the direction of an electric field and the relative strength due to a given charge. So the more lines are drawn for greater charges to indicate greater forces. So here you have two like charges. You can see the field lines repel each other. That would be the direction. If a positive charge was placed right here in the center, it would be going away from, or go kind of in the down direction, but they repel each other, whereas positive and negative charges attract each other. And you can see here there's double positive charges, which means there's more field lines here, which is the stronger the force. So let's watch a little video here on electric fields and test charges.
An electric field is a region of space around a charged object in which a stationary charged object experiences an electric force because of its charge. The electric field at a point is defined as the electric force that would be exerted on a small positive charge, called a test charge, located at that point. The electric force, like any other force, is a vector quantity. The strength of the electric field at a point is defined as the magnitude of the force acting on the test charge divided by the charge of the test particle, which is always positive. The direction of the electric field at a point is defined as the direction of the electric